Okay, I'm going to describe something real quick over here. I'm just going to be talking about translation of axis. What is really going on over here is that if you say we have x and y is the original coordinates relative to an origin point 0, 0, we want to translate it to a point denoted by hk in terms of the same axis. We want that to be the origin of a new translated axis, such that a point relative to that axis has x coordinates x bar and y bar. We get the relation over here that x is equals to x bar plus h and y is equals to y bar plus k, and you can see it pretty intuitively by the little drawing that I have over here, and you can see that xy is equals to the h plus the x and the y plus the y plus the k, So we're gonna be using this y to solve for this differential equation. So 1.05 m, and it's 8b. Okay, so basically what it says is that you have this differential function over here. You can see written over here: a1x plus b1y plus c1 dx plus a2x plus b2y plus c2 dy. Right, and we have this function, this differential equation, linear or differential equation with p of xy equals to this and q of xy equals to that. And how we solve this is basically we set the two functions, the two linear functions over here, and find their intersection point, and then we translate the axis to that intersection point, which gives us the relation that the translated axis x y is equals to x of the original axis minus h plus y of the original axis minus k, and h and k are the coordinates of the intersection point, and vice versa, of course. So if we reverse that, we get that x equals to x bar plus h, y is equals to y bar plus k, and dx is equals to dx bar, and dy is equals to dy bar. And then we substitute it into this equation, substituting in for x plus h, substituting in for x, you get x bar plus h, and substituting y for y bar plus h, y bar plus k, and you get this equation over here. And then you can basically rearrange the terms into this and this. And what can you see? Well, we defined that basically over here, these two are defining the intersection points. Now this one was relative to the normal untranslated original axis, but if you take this function and translate it to the h and k, because we know that this solution gives you that x is equals to h and y is equals to k, so using the relation that we have over here, right, that in this case this will be x minus h and y minus k, we find out that these two values are equals to what? Equals to 0. So these two values over here and this one is equals to 0 relative to the new translated axis. And of course here is the x bar and the y bar. So then we just get this function simplified, and this is a homogeneous not exact, but a homogeneous symmetric form with p and q both being homogeneous of order 1. So we can use the method for homogeneous coefficients for a first order symmetric form of a differential equation to find the solution. And that's it.